Okay, so in the PowerPoint they show you example 3.19, but I'm going to go ahead and show you how I worked it out. It's there for you if you want to look at it that way. So I'm starting with the dilution formula. C1 times V1 is equal to C2 times V2. Starting with my given information, so if we go to our textbook here, it says we have a 0.850 liter solution with a concentration of 5 molar copper nitrate, and this solution is diluted to a volume of 1.8 liters by the addition of water. What is the molarity of the diluted solution? So here I'm starting out with my dilution formula. I listed what was given to me. Okay, so I have the concentration of the concentrated solution and its volume, and I'm trying to find the concentration of the diluted solution with its volume. It doesn't really matter how you list it. You can list this information as C2 and V2. Again, you just don't want to mix and match. Okay, if the solution has a certain concentration, it has a certain volume, you have to keep these values together and label them either 1s or 2s. Okay. So anyway, so you're going to go ahead and rearrange the dilution equation for C2, okay, and then plug in the information that was given to you. And so you see here the diluted solution is 2.36 molar, which it should be. The original concentration was 5 molar, and it went down to 2.36 molar. So let's do another problem here involving dilutions. So example 3.20 is asking for the volume of a 0.12 molar hydrobromic acid solution. It can be prepared from 11 mils of a 0.45 molar hydrobromic solution. So they're asking what volume do you need to dilute the solution to. So here we don't know our volume. Our concentration of our diluted solution is 0.12 molar. Concentration of our stock solution is 0.45 molar hydrobromic acid, and the volume is 0.011 liters. So we have our dilution equation here. We're going to solve for, in this case, V1. Okay, so rearrange the equation. Substitute in our values here that's given to us, and the volume for our solution of our diluted solution should be 0.041 liters for the total volume of our diluted solution. All right, and so finally, the last problem here is asking for the volume of a 1.59 molar potassium hydroxide solution is required to prepare 5 liters of a 0.1 molar potassium hydroxide solution. So they're asking for the volume again. So here we have trying to find the volume. Molarity of the solution is 1.59 molar. Okay, so it is a concentrated stock, and the diluted solution has a molarity of 0.1 molar and a total volume of 5 liters. So starting out with our dilution equation, okay, solving for V1, so substituting in our values here, we get a volume of 0.314 liters for the volume of our diluted solution. Okay, so our last section, chapter 3, we're looking at other units for solution concentrations. We're going to talk about concentration units of mass percentage, volume percentage, mass volume percentage, parts per million, and parts per billion. And also perform computations relating a solution's concentration and its components, volumes, and/or masses using these units. So molarity is very useful for evaluating the concentration of solutions. In this section, we'll look at other units of concentration that are commonly used in various applications. So the first one is mass percentage. So the mass percentage of a solution component is defined as a ratio of the component's mass to the solution's mass, expressed as a percentage. Okay, so if you think about percentages, it's mass of a small piece over mass of the entire thing. So that's what you have with a mass percentage, mass of the component that you're looking at divided by the total mass of the solution times 100. So we're generally most interested in the mass percentages of solutes, but it's also possible to compute the mass percentage of solvent as well. So here we have a picture of bleach. This liquid bleach is an aqueous solution of sodium hypochlorite. This brand has a concentration of 7.4% sodium hypochlorite by mass. Okay, and so you can see when they give you the percentage here of the concentration of the sodium hypochlorite, it's by mass, and that means something. It's going to be different than for molarity, for example. We get to let's see. Let's first do a problem here from our textbook before we talk about this flow chart here. So in example 3.22, we're looking at determining what the percent by mass of glucose in spinal fluid happens to be. We're given the total mass of the sample of spinal fluid, and it tells us that it contains 3.75 milligrams of glucose, and they give the mass to you in grams as well. So here, when you look at this example here, we're given total mass, mass of glucose. So the mass percent, okay, is going to be the mass of the component divided by the mass of the solution times 100. So all we need to do here is take the mass of the component, which in this case is glucose, divide that by the total mass of the sample, 5 grams, multiply it by 100, and we get our mass percent, which for glucose, which is 0.075% for that solution. Okay, so going back now to our PowerPoint here, we can look at this flow chart here, and it's showing us how to go from the volume of a solution to the mass of a solution by using density, by multiplying by density, okay? And then going from the mass of a solution to the mass of hydrochloric acid, in this example, by multiplying by the mass percent as a ratio, okay? So we'll look at some example calculations of doing that. So I actually might try to keep this in the window here while we look at it. All right, so let's see here. I can do that. Squeeze it in. All right, so let me see if I can. So our next example here, example 3.23, we're given the density of a solution. Okay, the percent hydrochloric acid, which concentration is 37.2%. Okay. And they give us the volume of the solution to be 0.5 liters. They're asking for the mass of hydrochloric acid in the solution. Okay, so notice they gave me the volume of the solution and the density. So if you look at our flow chart here, it says if you have the volume of the solution, you multiply by the density to get the mass of the solution. Okay, so that's what I'm going to do here. The density is 1.19 grams per milliliter. Okay, I'm multiplying density times volume. Okay, look what happens to the units; they cancel out. You're left with mass. Okay, so this is the total mass of the sample. Okay, and so now going from mass of solution, we're going to want to go to mass of HCl. That's the question: how much mass of HCl I have for this solution? And so we're going to multiply the total mass times the percent of hydrochloric acid as a decimal. So in order to get, if you're wanting to find a certain number from a percentage, you're going to have to divide it by 100, right? So, which just brings the decimal place over 2 places to the left, and so you're going to multiply by 0.372. Okay, so that's what I did here. All right, to figure out how much mass I get from 37.2% HCl. And so my mass that I get is 221 grams of HCl in that solution, because 37.2% of it is HCl by mass, and the rest would be the solvent. All right. So here's another problem that's very similar. Okay. So going back here, looking at our flow chart here. So we're going to be doing the same process with this problem here. So let's go ahead and read the question. 3.24. It says rubbing alcohol is usually sold as 70% volume aqueous solution. If the density of isopropyl alcohol is 0.785 grams per milliliter, how many grams of isopropyl alcohol are present in a 355 milliliter bottle of rubbing alcohol? All right, so notice they gave us the percent of alcohol in the solution. Okay, they gave us the density of the solution, and they gave us the volume. So those three things, just like they did before. And so here I have the information listed out. Okay, so here's the density of the solution. They're again asking for the mass of isopropyl alcohol. Before it was hydrochloric acid, but same concept here. They give us the total volume, 355 milliliters. The percent alcohol, isopropyl alcohol, is 70% by volume. And so here all I need to do is take the density of my solution, which is in grams per milliliter, okay, multiply it times the total volume of the solution. Okay, so our units here are grams, so we get 278.68 grams for the sample. Okay, that's the total mass there. And now all I have to do is, like before, since it was 70% alcohol, converting this percentage to a decimal, multiplying it by the mass is going to give me the mass of the isopropyl alcohol, which is 195 grams. Okay. All right, so going back here. So we talked about mass percent. Volume percentage is the same idea, except for it's relative to volume and not mass. Okay, so the concentration of a solution formed by dissolving a liquid solute in a liquid solvent is often expressed as a volume percentage. The volume percentage is the volume of the solute divided by the volume of the solution, the entire thing, times 100. And so you also have mass volume percentage. The mass volume percent is a ratio of a solute's mass to the solution's volume expressed as a percentage. The specific units for the solute mass and solution volume may vary depending on the solution. For example, physiological saline solutions used to prepare intravenous fluids has a concentration of 0.9% mass per volume, indicating that composition is 0.9 grams of solute per 100 milliliters of solution. Okay, so you're going to see this in medicine here. We have mixed mass volume units are commonly encountered in medical settings. Sodium chloride concentration of physiological saline is 0.9% mass to volume. Here we see a glucose meter. So this device for part B measures glucose levels in sample of blood. The normal range for glucose concentration in blood is around 70 to 100 milligrams per deciliter. Okay, so you can see the units there. It's mass per volume. So depending on what you're dealing with, is going to dictate what type of units you can use for the concentration. All right, so parts per million and parts per billion. So you probably have heard of this before, if you've ever looked at research papers involving pollution. Okay, so a lot of data is gathered, and there's certain, the government puts out certain criteria for certain amounts of for example, lead in the water can only be a certain percent, or parts per million or parts per billion value. And so you've probably heard of this type of concentration before, this variation of concentration. So very low solute concentrations are often expressed in parts per million or parts per billion. Okay, so the formula for parts per million is mass of solute over mass of solution times 10 to the 6th power. And then for parts per billion, same formula except it's times 10 to the 9th instead of times 10 to the 6th. Okay. So here we see a picture of water coming out of a faucet. It says trace level concentrations of contaminants can render unfiltered tap water unsafe for drinking and cooking. And so it has a picture here of your inline water filter. Reduces concentration of solutes in tap water, and so a lot of refrigerators have this built-in filter that you can change out periodically, so that the tap water that's used to make your ice in your refrigerator or dispensed water out of your refrigerator is cleaner than regular tap water. Alright, so we have one more calculation for Chapter 3, okay, and that's example 3.25. Alright, so here it says, according to the EPA, when the concentration of lead in tap water reaches 15 parts per billion, certain remedial actions must be taken. What is the concentration in parts per million? Okay, so if we compare the two formulas, like we just saw earlier, we're looking at the two formulas. If the EPA's value for lead can exceed 15 parts per billion, what is it in parts per million? Well, how did I get this number? If you compare the formulas for parts per million versus parts per billion, the only difference here is the exponent here. 10 to the 6th versus 10 to the 9th. That's 1,000 times difference. Okay, so so all I have to do then, if this is parts per billion, to find parts per million, I'm just going to move the decimal place over 3 places to the left. And that's what I did there, to find parts per million. Okay. So the next part of this question, okay, because that first part was pretty easy. At this concentration, what mass of lead would be contained in a typical glass of water? So here it says 300 milliliters, so that gives us the volume. So going back to our problem here, so here we're dealing with a concentration of 0.015 parts per million. All right, and so let's go back here to our original equation. So parts per million is equal to the mass of the solute divided by the mass of the solution times 10 to the 6th. Right. So I'm going to substitute in my parts per million concentration, which is 0.015. So I did that here. Okay. And then the mass of the solute, that's my lead. I don't know that, so that's just an unknown. That's a variable there. And then the mass of the solution, okay, is 300 grams. So how did I get 300 grams? So notice that the mass of water was 300 milliliters, right? And so whenever they're talking about a glass of water here, so if we have 300 milliliters, the density of water is 1 gram per milliliter, so that means 300 milliliters is 300 grams. Okay, so that's my total volume for my glass of water. So that's how I got the 300 grams there. Okay, and now all I'm going to do, now all I'm going to do is just cross multiply. Okay. All right, so I can cross multiply. But before I do that, actually you see me rearrange this because you have this fraction here times 10 to the 6th power. All right, so I brought this over here, divided both sides by 1 times 10 to the 6th power. Okay, and then left this here. I'm just writing it as x instead of mass of solute. Okay, over 300, and then I cross multiply. Okay, and I get 4.5 times 10 to the 6 grams of lead. Well, they didn't want it in grams. They wanted it in micrograms. So I have to do one more final conversion. Okay, no problem. So before I had 4.5 times 10 to the negative 6 grams of lead. And now I need to convert it to micrograms. Well, 1 microgram is equal to 1 times 10 to the negative 6 grams. Okay, and so when I do the math there, I get 4.5 micrograms of lead.